Hi, everyone. We're going to start our next session. Our next session will be presented by Brian Richardson from Intel. He'll be speaking today on hardening firmware components with host-based analysis. And I think most of you know Brian. You need the microphone.
Thank you. Let's talk about firmware. One of my favorite topics is testing, not because I like reading bug reports and realizing that I did terrible, terrible things in the name of booting your system, but because I'm actually a proponent of actually trying out your code before you unleash it on the world. I believe that release is a term that you use kind of like doves at an opening of an Olympics and not like a bear escaping from the zoo. So let's talk a little bit about philosophy towards firmware development. And the thing is, it's a hard job because firmware, first of all, firmware should work without people noticing what it does. It's supposed to be kind of invisible thing that does its job and moves on with its day. So as somebody who works marketing an organization that's designed to promote firmware, it makes it kind of difficult. It's kind of like advertising ninjas. Like the ninjas you see are probably really bad at their jobs. So I want to kind of keep us out of that problem space. The thing is that we're essential to booting the system. We're low level, but most of your testing's done at an integration level. Why is that? Because you're using it to boot a thing. And so you integrate it into the thing with all the other things that help the thing boot, and then you test all the things together, and something breaks, and you don't know which thing broke the thing. I hope you followed along with that. It disappears into dozens of other components that you've written, and then you're trying to go back and say, I don't know what failed. So I actually got an email from a colleague a couple days ago, and I said, yeah, I'm getting this crash at this postcode, which doesn't really mean anything anymore. And the crash is coming from this function, and the function's in MDE module package. What does that mean? Anything in the firmware could have done that because it called something badly, and then he doesn't have enough trace information to go back. So he integrated a component somewhere, it's totally broken, had no way of proving that it had some basic fault before he integrated it. So it's really not ideal for discovering issues with new drivers, and it's really not ideal for discovering vulnerabilities. So this is kind of a security talk in some ways, because of the types of issues people tend to target are the ones that get them the most value. So you have the two kind of sides of figuring out if your firmware is broken. The one side is all the responsible people in the room right now, hi, thanks for coming, who have decided that they want to test their code and make their products good before they ship. The other folks have decided that they can potentially get bug bounties for figuring out if the people in this room didn't do their jobs. Those people I'm a little concerned about. So we have tools that are focused on security testing. We have ChipSec. That is a tool that's been out now for 5 years. It's an open source framework, and it analyzes platform firmware and hardware configuration at runtime, and that's the key part, at runtime. ChipSec really measures artifacts. It looks for things that say this is in its best possible configuration from a runtime standpoint. That bit is set correctly. Now you may have taken the dumbest possible path to set that bit, and if you get in the middle of that path, that bit could go awry. But the bit's fine. Bit's perfectly safe. Code coverage. Did I actually test all the code that I have? There are tools like that. We have a test harness we've been using for years called Intelligent Test System that has code coverage built in. So when you run a test case, it has a way of saying you exercise these paths. You did all the ifs, you just didn't do all the elses. So maybe you should go back and write a procedure that does the else. And then you have symbolic execution in virtual platforms. Now that doesn't really solve the platform-specific nature of firmware, but it does give you a way of exercising certain things. I cannot enunciate today. So we have a project called Excite, which we're moving towards open source. That uses symbolic execution fuzzing. It's primarily targeting SMIs, which are a really difficult thing to debug properly. These are all really great, but they're primarily integration tools. So I would like to beat up the driver before I put it in the system. I'm not going to be able to do a lot of functional testing on it, but I can at least look for kind of stupid things that end up being the expensive migrations when they're in the field. I can check for basic kind of input validation. So let's look at a kind of common problems. One is fuzzing. So fuzzing is abusive inputs. A guy walks into a bar. 15 guys walk into a bar. Minus 3 guys walk into a bar. 3 dogs in a trench coat walk into a bar. That's kind of your fuzzing. Can I take an API and abuse it? Now, it's not going to fix integration, walk into a bar, ask where the restrooms are, the bar catches fire, right? That might have been out of scope for your unit test. We'll worry about that one later. So, address sanitization. Just your standard memory nonsense that gets you in trouble in a lot of applications. Code coverage. Did you actually test all the things? So just within that particular one component, am I able to show I have a high percentage of coverage from these unit-based tests before I drop this in? So there's a challenge here. How can a firmware development do this without doing it on the platform? Can they do it in an OS-based environment? So I'm already developing under Windows, under Linux. While I'm here, can I just go ahead and exercise the unit test on this component before I hand it off to a developer? Now, of course, I've got like 20 minutes left, so I'm not going to say no at this point, because then I just sit down and finish my lunch, and you guys get some peace and quiet for a few minutes. Of course, I'm going to say yes, because we've developed a tool that we're going to release into open source called Host-Based Firmware Analyzer, or HBFA, because everybody wanted an acronym for this thing. Sorry about that. All the cool names are taken, by the way. Redfish, really cool, already taken. Expensive to trademark. The idea of this is that if I've talked about these, ideas of like code coverage and address sanitizing, then somebody who's done OS or application development has said, well, yeah, we already have all this stuff. Why is firmware so late to the game? Well, because firmware is operating in its own weird little environment on the machine, and these OS tools typically aren't available to the thing that boots the OS. So what we've done is created a way of testing firmware drivers that are based on UEFI in the developer's own environment. And this, rather than reinventing the wheel, we're just making a hub to attach existing wheels to. So in this case, we're going to take the existing tools you have for sanitization. So AFL, libfuzzer, Peach, symbolic execution using CLE. CUnit does automated unit test execution. We already have the tools in the world in open source that do these things. But now we've essentially built as a test harness that allows you to apply this to PEI and DXE components before you unleash them on the world. Doves versus bears. Right now it's running in Linux. We do have an option for running it in Windows as well. The screenshot is from Ubuntu. And the idea would be that we have not only ways of just doing these basic tests, but how do we instrument or do fault injection or do tracing to figure out how we fix the silly things we do in code before we give them to other people. Okay, so case designs are usually based on just having an entry point into a component. You pick a framework, so I'm going to say, oh, this is a test for AFL. And then you have a way of triggering a particular function. So this determines what kind of input you're passing, which part of the unit test that you're executing, and then the stub that you need to run this and invoke and collect the results. In one of the cases that was designed, we're doing this with USB main. So in this case, we want to test USB main. We're looking at a particular area. Let's take the host controller stub. So this USB I/O PPI stub. And we built a specific USB build description table. And we're triggering a test based on that particular point. These are somewhat customized to the actual idea of what you're doing because it's a unit test. Integration will figure out if when you plug the USB device in, does it actually work? But at this point, you just want to test the driver and the APIs that you've developed. Of course, to prove that it works, somebody took a screenshot and drew a circle around some things. So this is the output of AFL, which is American Fuzzy Lop. It is a existing fuzzing tool that's used a lot in Linux development. So this is from the BMP support lib, i.e. the thing that makes the logo show up on your screen. Because that's taking input that could be substituted in a table, it's a popular thing for people to try to attack. Can I, instead of inserting an image, insert executable code? Okay, so the thing that we wanted to show on this was the execution speed. And reading these results are a little complicated, but the idea is that this runs really fast compared to doing the equivalent number of, can I exercise these individual functions somehow in the middle of the firmware while it's integrated with everything else on a system that's only really single-threaded and has to reboot and recover from a power standpoint, versus can I just beat up this interface over and over again in my OS, which is multi-threaded and has tons of RAM. Peach is set up in kind of a similar way where, I'm trying to remember what this test case is, but this is doing a lot of, this is things like zero pool and malloc, so this is beating up on memory sanitization and address sanitization. Now these results, hard to read, so of course, we made a test log. The idea for the test log is that what you want to look at is what cases failed, where are my trace information, how do I get back to where the failure occurred. So this is trying to, again, take these multiple types of test harnesses which already exist for the operating system, for the driver environment, and figure out how to take the appropriate information out of them and apply it to firmware unit testing. Now, because we already have this used in-house at Intel, we made a decision that this was going to be open sourced, and we were also going to open source the test cases. One thing that I've discovered working at Intel and trying to sort of gently nudge us towards doing more things in the open is that we are great at releasing code. Documentation, it comes out. Test cases, very rarely. So if you can't actually prove how somebody validated something in open source, have you filled out all the trust obligations to doing things in open source? Just releasing the code itself is just saying, here's a starting point. But we did some testing internally. We can't release 100% of that because some of the people I work with are lawyers, and we have some things that are proprietary to our systems. But can I release a high percentage of that? Because if I trust the code enough to put it out in the open, why don't I just show you how I came to that level of trust? So we're going to have a test database based on common issue categories. So the 8 that we've selected are external input, race condition, hardware input, secret handling. That doesn't mean we're not going to tell you how it works. That means you're handling things like TPM data or runtime variables that deal with things like, secure boot. Register locking, configuration, replay and rollback, so that you can stop rollback attacks, so you can stop replay attacks, so you can stop replay attacks, so you can stop replay attacks, and then cryptographic and key functions. The idea behind this is that, again, we want to get the really, and I hate to say this in front of a bunch of programmers who have all done this, but were well-meaning when they did it, just really dumb things. A lot of things that get us on the stage at Black Hat, not in the fun way, not the I am here to give my TED talk, but in the, ooh, I know the guy who wrote that code, that's unfortunate, gets us into those situations are just usually stupid. Let's be honest. It's just we didn't do a particular check. We forgot what kind of variable type we had. We passed in a 0, we subtracted 1 from it, and it turns out that that was an unsigned integer. That's a real thing we were talking about this morning. So you get that kind of stuff eliminated very quickly. And we do it, again, if we're going to put stuff out in the open, let's just acknowledge what other people have contributed before us. It's not stealing if it's open source, kids, as long as you obey the license. So you're incorporating something that people have proven for years already works in an OS environment. How do you incorporate that? And the way we've designed the test stub and test harness to essentially wedge these things into an OS environment and exercise the inputs and outputs, that's what gives us the advantage. We didn't say we came up with a new fuzzing technique. We're saying is we found a way to take existing fuzzing techniques and apply them in a unit test environment. It's extensible. We know we didn't cover everything, right? This is a starting point. And by getting it out into the open, we're hoping that other people are going to contribute to that, put things back into that same test case database. And hopefully the ecosystem uses it. Again, one of the things that we're trying to do more is not just show that, oh, we put code out. Ooh, code, lines of code, that's amazing. That's a metric a lot of companies use. They tell you, I've put out lines of code. They don't really measure the metric on how many of those lines of code you had to fix later on, or how many lines of code you've been removing because you realize that some of the code that's in there really isn't necessary and you should take it out. And one thing I do want to note on this, even though that I'm going to be pointing to an Intel branded white paper, the name Host-Based Firmware Analyzer does not have Intel registered trademark in front of it. We know this is going to be a cross-architecture piece. It's part of Tiana Core. It's not part of Intel. So that's a thing that we're going to be contributing up into Tiano Core, into the EDK2 test environment. But this is designed for us to bridge a gap. We've had this integration versus unit testing gap in firmware since firmware. And we've tried various things, mostly simulation products, to try to get around that. But at the end of the day, we really need better tools for checking, is this individual unit of code as healthy as we think it can be before we unleash it on the world? Okay, so that's great. Brian just blathered over some PowerPoint again for 15 minutes. What do we do about this? Okay, first, we're going to release this in Q2, and this is, it's not real Q2, it's marketing Q2. I was hoping for April. It's probably not going to be April. But we are planning to release this. We have shown demos of this at RSA. We have gotten some partner feedback early, and I'm trying to get a few other partners to look at it and give us some comments before we put it out into the open. Just to get it as close as we can to, a usable beta for a lot of people. It will be in the staging branch initially, and then once we determine that it's good stuff, we're going to move it from staging into the main EDK2 test. TianoCore.org already has a wiki page up. We've written a white paper that goes into more details about the test strategies. If some of the terms look familiar, it's because I wrote both this presentation and a lot of the white paper. But that gives you some concept of what we're doing and how you can look at applying it to your development environment. And with that, oh goodness, I left time for questions. That's unfortunate. Okay, at least it wasn't Gary. All right. I regret saying this, but somebody give Andrew a mic.
No, I'm just curious about the granularity of what you're testing. Are you testing a driver? Are you grabbing chunks of the driver? Because you had the USB example.
Yeah, we're testing a driver. So essentially, you can test a .EFI with this, whether it's PEI or DXE.
And so is that the same binary you'd run on a real system?
Yes.
Okay. So how do you deal with things like providing all the EFI services?
So this is essentially a kind of an EFI stub that you slip the driver into. It's not going to exercise 100% of the functions that are inside of it, because there's some things that say, oh, I need to call out to this very specific function way outside. I think that's out of bounds for the test cases. And that's one thing we do have to work on in the documentation, is making sure we set the boundaries for, you can test these things, you probably shouldn't try to execute these functions.
So you're testing more on like a protocol level then?
Yeah.
Okay.
Yeah, so we're not seeing, does the driver actually touch the hardware, because at that, where we're executing, and you don't want the driver to touch the hardware, but can you make the driver do dumb things, which are harder to kind of factor when you're in a full environment.
So basically the test harness then has a set of generic stuff faked out, like like the GBS, GRT kind of stuff.
Yeah.
And then you have to supply a given protocol to drive test cases through.
Right.
Like
and your
in
test
example,
case.
So
yeah.
you were providing lower level USB functionality and maybe higher level USB functionality, so you could test the piece in the middle.
Yeah, you're really, it's not as much testing USB functionality as it is testing how this talks to the protocols it's supposed to interface with.
Okay. Thanks.
You've run this host-based, anyways, this test application a number of times before. About how much time does it take on your systems to run?
The time it takes to execute is going to depend a lot on how robust your test cases are. We're usually talking about seconds to minutes kind of range to execute all of the test cases, rather than, I'm going to put this thing in the harness and go home for the weekend and let it reboot over and over again. But most of the people are talking about, once they get to execution, they're running their test in some span of minutes.
So it's reasonable in this case for an application of this that we could put it in continuous integration testing
Well, putting this in integration testing, it's kind of the wrong environment. Like, this is really designed for a unit-based test because you're testing an individual, like one unit O code, like a .EFI. So this is not designed to plug your entire runtime firmware into. So integration testing, I think we have possibly too many ways of doing that right now. Like, I know within my team, we're actually trying to cut down the number of test frameworks we have because we're having trouble kind of having, this group used framework A, this group used framework B and C. And we're like, well, then our results don't match and our methods don't match. We're trying to get to a common one for integration. For unit, there's not as many of these floating around.
All right, appreciate it.
So I'm curious, can I use this thing to test libraries rather than the DFI files?
I don't think so, but I'm not entirely sure. That is a follow-up. So let me check on that. All right, now you got to make Harry run to this side of the room because.
I think this is great. Thanks for making it open.
Oh, sure. You should really thank people like Jaywin and Chris and folks that actually wrote code. But all right, get to Harry on your way back. Get to this guy back here. He keeps. Harry's got to get his steps in.
Give somebody else a chance to talk, right?
Yes, you can test libraries with it, first
Okay.
of all. This is not critiquing the decision making, but what was the actual process that caused it to take this long to release?
There's a process within Intel for clearing things for open source, and part of that was the issue that you have with this is that since we're taking things and saying, okay, the AFL, for instance, has one license, Peach Fuzz has another one, so we have probably like a dozen things that we're using that have their own licenses that are not BSD or BSD 2+ patent. Because of that, they have to do a lot of analysis to see, are we accidentally cross-linking something? So if we were, say, working with something that's GPL, and we're supposed to be a BSD license for the surrounding framework, and if we link those two improperly, a lawyer suddenly appears that's super effective, right? That doesn't go well. And we're trying to make sure that we're doing this clean. And then within any large corporation, you have to make sure that you haven't done an accidental IP leak, which actually, honestly, isn't the thing that took the longest this time. It's that first one of trying to make sure that we're interacting with these other licenses and honoring them properly.
Okay, that makes sense. So even if you had started it in the open from the get-go, it would have still taken a lot of time for this evaluation.
Yeah, and I'm going to be honest, you can see some of the stuff that Dong was talking about this morning that he said he gleefully lifted from Mark's presentation. That is kind of our philosophy of we're trying to do more things in the open day one, and there are a lot of programmers that don't really understand what that means. And that's not just an Intel thing, that's at a lot of companies. Once I open source the code, it's going to be free and woo, and the hippies will love it. We're like, no, that's not. It's not just getting the code out in the world, it's making sure that you're developing the code in a way so that a community can maintain it and use it, and you're transparent to that community about why you did it and how they can contribute back.
Right, yeah, it's way harder than it seems at first.
It's a little, it was so hard I hired a guy, so it's his problem now.
All right, thank you.
Sure. All right, get Paul back here, he keeps raising his hand. Don't let Gary grab the mic on the way over. Just.
Simple question, OS support and processor support. Does it only work on Intel processors? Could it work on an AMD processor perhaps, or an ARM processor? And does it run under Windows, Linux, and Mac?
Let me take the second one first. Right now it runs under Windows and Linux. There's nothing that I think is preventing the concept from running under Mac, but I think it's more of, are the tools that it relies on available for that? Because again, we have external dependencies on, do these tools run on this particular OS environment? The second part, he went all the way over there, so I got to change my eye line. The second part of that, you're talking about processor support. So you've got two kinds of processor support. One is the actual host system that executes the test. And right now, we've done it on Intel processors, obviously. But if the tools, we already know that the EDK2 framework itself runs on Linux, Mac OS X. So we think that if the tools are there and they'll run on these other processor architectures, it should be fine. because we know obviously you can build on ARM because they're here. Hi guys. What the tests run on, that's again more of a what did you compile for and what do your test cases do. I don't see any reason why you couldn't fuzz an ARM binary using this, because everything else seems to work on ARM. Why doesn't this? So again, it's a good thing this is going to be open source, because for some reason I don't plan on testing those. I don't know why. But once it's open, I really want people to see, because there are test cases that we've seen on ARM that you actually catch the reason why they fail. We're on an Intel system, they just die in a fire. We were talking a lot about null pointers. Art and I had this conversation at the last Plugfest. They're catching null pointer exceptions that you don't get on Intel platforms because they don't always have memory at 0, and we always have memory at 0. And so this thing will just gleefully go, there's memory at 0, let me play with that. And sometimes it's non-trivial and it doesn't do anything, or sometimes the system explodes. Whereas in an ARM system, it'll just go, nope. And then you're forced to deal with what happened. And the other driver got an array size wrong, and it went off the end of the array, and it's in 0 land. Ooh, 0 land. And there's no memory there, and their system dies. So this whole collaboration across architectures thing, I'm cool with it. All right, you're probably the last question, so let's go with that.
So you mentioned that this works with AFL and libfuzzer. Does that then require source access so you can properly instrument for code coverage, or can you just drop in a black box binary?
I believe it requires the source for code coverage. I mean, normally you do require source for code coverage, but it's a unit test, which means the developer's usually doing it, and I hope you have your own source. I mean, some environments are so secure, maybe you don't, but it is really designed more for the unit test idea of the developer or somebody who's at least knows the developer well enough to get their code to work on it. All right, I'll be around at 3 o'clock for the speaker hours. Thanks very much for the questions, and thanks for coming.